All right. So we got two cars. We got Amanda's car and Bertha's car. They both have equal masses, so the mass is the same for both cars. Okay, Amanda accelerates in 2 seconds, as does Bertha. Amanda goes from 10 to 20 meters per second. Bertha goes from 20 to 30 meters per second, again in 2 seconds. Okay, so they're asking, is the work that Amanda's car does while speeding up greater than, equal to, or less than Bertha's car? So in this case, the work is equal to, well, in all cases, work is equal to the change in energy. But what kind of energy? Not gravitational potential, not elastic potential, but kinetic, because the speed's changing. So this would be KEF minus KEO. So that equation's not in your equation sheet because you're supposed to be able, what equation is work equals the change in energy, specifically mechanical energy. Okay, remember mechanical energy is kinetic energy plus gravitational potential energy plus elastic potential energy. But in this case, we only have the kinetic energy that's changing, because the only thing that's changing is the speed. Okay, so let's just work this equation out. mvf squared over 2 minus mvo squared over 2. So basically we're looking at VF and VO. So m over 2 times VF squared minus VO squared is what the work is. Well, that's what the change in kinetic energy is, which is what the work is. So just work it out. So you can see if you plug numbers in that Bertha's VF squared minus VO squared for Amanda is equal to 20 squared minus 10 squared, which is equal to 300 meters per second. Whereas for Bertha, the VF squared minus VO squared is equal to 30 squared minus 20 squared. That'd be 900 minus 400, which is 500 meters per second. So just looking at this equation right here, you can see that m over 2 is the same for both Bertha and Amanda. But because Bertha has a bigger VF squared minus VO squared, which is 500 compared to Amanda's, which is only 300. But so therefore, Amanda did less work than Bertha. So my answer would be Amanda's car does less work. Okay, so what car is more powerful? Okay, so the way we're going to do that is power equation is work over time. And we have the work already. We know that Bertha's work is bigger than Amanda's work. So if the work is bigger, and they're doing it in the same time, they're accelerating the same time, 2 seconds, like I said before. So they're doing the guy who does more work in the same amount of time is more powerful. So that'd be Bertha. So Bertha's power is greater than the power that Amanda has. Just like, because the work that Bertha does is bigger than the work that Amanda's car does. Okay, so this next problem, I put all the information on the picture here. Okay, which girl did more work to go up to the top of that thing, the hill? They both started at the same level, right? So work in this case, the work is the change in energy in all cases, but in this case, it'd be the change in GPE. We're assuming that the girls go the constant speed up. Did I say that? Okay, so after they do a very short acceleration from rest, they're going at constant speed up. Then they do a very short acceleration to stop at the top. That's so small, it doesn't matter. Okay, so really the work they do is the change in their height, gravitational potential energy. So that would equal mgHf minus mgh original, because GPEF minus GPEO. Now the height at the beginning is 0, so we can cross that out. So we can just say the work equals mgHf. So which girl did more work? Well, Abby and Bonita, I guess. So work of Abby is her mass times G, which is her weight, 700 mgh, and HF is 30. And the work of Bonita is 100. Oh, sorry. Her weight, mg, is 500 times her speed. No, times the height. I'm just looking at this equation right here. Times her height is 30. So this is 15,000 joules. You didn't have to word this. This is 21,000 joules. Okay, so obviously Abby did more work than Bonita in this case. Which a girl exerts more power. Okay? So the power is work over time again. So the power of Abby is her work, 21,000, divided by the time it takes, 40 seconds. And then the power of Bonita is 15,000, divided by her time was 20 seconds. Okay, so you can see that Abby, even though she's doing less work, Abby's doing more work than Bonita, because she does it in a longer time. It works out that her power is 525 watts, which is less than 750 watts, which Bonita did. So the power of Abby is greater than the power of Bonita, even though Abby did more work. Okay, I'm going to skip number 3 because it's exactly the same kind of idea. I'm not going to do it. Okay, so number 4, Blocks slide down a frictionless incline. All masses start from rest. So I know KE1, initial KE is 0 for all these cases. We have GPE1 equals mgh. Okay, so what we're trying to do is rank the kinetic energy of the sliding masses at the bottom of the incline. So GPE, using conservation of energy, there's no work lost as friction or drag. So using this equation, we're looking for KE2 at the end. So that equals GPE, which is mgh. So what we do is, these are the masses. You take the mass, multiply by 10, and then multiply by the height. So GPE is equal to 10 times 1 times 10 is 100 joules. This guy, GPE, is mgh 1 times 2 times 10. 1 times 20 is just 20 joules. Okay, this one, the GPE in case C is equal to mass times height times G. So 10 times 10 is 100 joules again. Letter D, GPE is equal to mass 1 times 0.5 is 0.5 times 10. That's only 5 joules. Letter E, mgh, 50 times 0.5 is 25 joules, is what the GP is. And then finally, letter F, 15 times 7.5, or 0.75 times 10, I get 112.5. So we're asked to order the kinetic energy at the point that they reach the bottom from greatest to least. Okay, so again, kinetic energy is equal to, where is this? Kinetic energy is equal to, at the end is equal to GP at the beginning. So we can say, well, I just figured out GP, so that's equal to the K. Oh, so who's the biggest? Looks like letter, wasn't there one that was two? Okay. Letter F's the biggest, it looks like to me. Then there's a tie between A and C. And then there is, let's see, 20. Then E is next. Wait, who am I missing? A. Okay, I got 25, 5, and 20. Okay, so E is next. And then comes B with 20. Then the smallest of them all is D. Okay, so this one, 100 Newton box. Okay, that's the weight of the box. It's at rest. So KE initial is 0. Horizontal force. So that's just the force of push. What's the work done by a student if the force applied is shown for 5-meter trip? Okay, work equals F times D. If you look at the first equation on the equation sheet, is F delta X cosine of theta. The theta is the angle between the displacement and the applied force, the displacement and the applied force. That angle is 0. So cosine of 0 is positive 1. So I just skip out the cosine of 0. So it's be 80 times 5, 80, the force, 80 times 5, so that'd be 400 joules. What's the change in kinetic energy of the box due to this work throughout this trip? Well, the change in KE equals KEF minus KEO. KEO is 0. So, or KE2 minus KE1. Okay, so that'd be M. Wait, I don't have to do any of this, because the work I did was a change in K. I already found the work equation. So this would just be work. The change in KE is equal to the work. So that would equal the same as what I have up here, 400 joules. Okay, so now this 80 Newton force is not pushing it anymore. Okay, but the surface is rough and the coefficient of kinetic friction is 0.4. So coefficient is 0.4. What is the friction acting on the box? Okay, this is the last equation, an old one that we've used before. So friction equals mu times n. It's the very last equation on the equation sheet. So it equals 0.4. And the normal force on the box is equal to the weight because it's not on a ramped surface. And the weight is equal to, well, we already have the weight up here. It's the same box. It's 100 newtons. So my answer here is the friction is equal to 40 newtons, 0.4 times 100. Okay, this next one could screw you up. So what's the change in kinetic energy? So I'm looking for a change in KE. Okay, so that's KEF minus, let's say KE2. Let's just do it that way. KE2 minus KE1, or KEF minus KE original. Okay, so I know KEF is 0 because he stopped right there at the end. So basically, the change in KE is what it had at the beginning, the kinetic energy, but negative. So it equals a negative KEO, and KEO we solved up here to be 400 joules, right? Okay, so we did that thinking already. Okay, can you have negative change in KE? Yes, if the ending energy is less than the original energy. Okay, letter E, what is the work done on the box by this friction? Well, work. Okay, you just found change in KE, right? So what kind of work is it? Frictional work. So work done on the box by friction is this what I just found? Negative 400 joules. That's what we found down here. How far a distance does the box slide on the rough surface? Okay, so no, work due to friction is equal to friction times delta x d times cosine of theta. Theta is between the box moved this way, but the friction acts this way, so the angle between those two forces is 180. So cosine of 180 is -1 FD cosine of theta. So I don't even think that out. I just know if it's friction, it's negative work. So let's plug it in. I got WF. We just did it. -400 equals negative, what's the friction? We solved that to be up here in green, 40 times the distance traveled. So the distance equals -400 divided by -40. So that comes out to be the negatives cancel out. So that comes out to 10 meters. Okay, let's continue. Now, instead of a rough surface, after traveling to 5 meters, smooth surface, the smooth surface continues a frictionless incline. How high would the box get before it stopped as it continues sliding up the incline? Okay, so how high does it get? Okay, so right here we have KE1. We have no friction, so I'm not going to subtract WF. And at the end, it stops before it slides back down. So that's GPE because there's height. So, but you know, I already know what KE is 400 from before. This is all the same problem. So, MGH. Okay, so mg is, what's the weight of the box? 100. That's what mg is. Equals 100 times h. So we know that h would equal 400 divided by 100, or 4 meters. What's the K and the GP of the box? One is 75 centimeters above the level. So what if it got to be, what if it got this high right here? What's this GP and what's this KE separately? So before, KE1 would equal KE2 plus GPE2. So we know KE1 is 400 still. We don't know what KE2 is. I can't solve it because I don't know what V is. So we better be able to solve for GPE. Well, GPE is mgh2. So that would be the mass times G is the weight. That's 100 given before. Times the height is 75 centimeters. Be sure you change that to meters by dividing by 100. Okay, that's the height that was given. So I know that the GPE2 is 75 joules. 0.75 times 100. I know KE2 would just be 400 minus 75 joules. Okay, so to find KE2, we just subtract those guys. So that's 325 joules. So K2 is that, and GPE2 is 75 joules. Okay? Going on 7 incline at the end of the 5 meter friction-free level surface, there is a spring that will compress and stop the box. Okay, assume no heat loss. Okay, so instead of incline, there's still no friction, but now we have a spring. Okay, if the spring stops, what is the change in the spring potential energy of the spring? Well, so I'm just going to treat this like energy conservation. So KE1 plus EPE1, which I don't have any, but you'll see why I'm doing that, equals KE2 plus EPE2. Okay, so I'm looking for the change in EPE. So KE1 minus KE2 equals EPE2 minus EPE1. So I know that KE2 is 0. So KE1, we already know, is 400 joules from before. EPE2 is something, but EPE1 is nothing. So I I know EPE2 is 400 joules. Now I'm asking for the change in spring potential energy. So the change in EPE is EPE2 minus EPE1. Well, I know EPE1's 0 because the spring is not squashed. So, so there's my answer. The change in EPE is equal to 400 joules, plus 400 joules. Okay, as the spring compresses in 7 centimeters to stop the box, what is the spring constant? So you might want to be tempted and look at the two equations for spring constant that have spring constant in them. Okay, I don't want to use the first one because I don't have any forces. I mean, I could find it, but it's kind of a hassle using other chapters. Okay, so I'm going to use this one right here. Now, I know EPE2. I know EPE2 is going to be 400 joules. The K is what I'm looking for. The distance it got squashed in is 7 centimeters, which is 0.07 meters divided by 100. Squared over 2. So K equals cross multiply divided by 0.07 squared. So I get 163265. I'm just going to round that up. 160,000 newtons over meters is the unit for newtons over meters, not newton meters, is the unit for K. What is the average elastic force provided by a spring in order to stop the box? Okay, I gave you this equation right here. But the negative doesn't really matter. It's just telling you that the force and the displacement on a spring are opposite directions. So you can ignore that part. So I'm looking for the average. Okay, really, this is the maximum force. Maximum force. Elastic force. So I didn't put that in my equation sheet. You might want to add that. Now, so the K we just found was 160,000 times the displacement is 0.07. And I'm getting 11,200 newtons. Now that's the maximum force. Okay, so that's when it's all the way squashed. The average elastic force is what you started out force plus the final force divided by 2. So the original force, when you're pushing a spring, the original force is, at the moment it touches, there's no force, and then it increases gradually, increases smoothly to the maximum force where it stops. So F average is equal F max, F2 plus F1 divided by 2, but F1 at the beginning is 0. So really this is just the maximum force divided by 2. So my answer would be average force is equal to 5,600 newtons. What is the elastic force on a spring at the moment? It's as maximum compression. Really, I should have done L first, and that's 11,200 newtons. I did that right there. Okay, then we have some graph stuff. What was the net work done on the object based on its F versus D graph? Okay, an F versus D graph, the slope doesn't mean very much of anything, but what you have to do is the area between the graph line and the x-axis is equal to the work. The total work, capital W. Now, this you can have positive work or negative work, right? So first break this up into shapes that you can find the area easily of. Okay, so this area right here, and then this area right here, this area right here, and this area right here. Okay, so we'll just find all those areas. This is area 1, which is work. The work done it. Okay, so that'd be 3 times 2 equals 6 joules. Okay, how about this area right here? Area 2 equals, the height is 3, the base is 5 minus 2 is 3. So 3 times 3 divided by 2 is 4.5. Okay, so base times height, 3 times 3 divided by 2 because of the triangle. So that'd be 4.5 joules. Okay, let's do this guy right here. That little one, area 3, is base, which is 1, times the height is 1 divided by 2. So that'd be 1/2 joule, 1/2 joule. But it's really negative 1/2 joule because it's negative work because it's underneath the graph line. It's underneath the graph line. Okay, and then finally, this little piece right here, A4 equals work 4. I should have said this, work 3. Work 2. Okay, so that is equal to 1 by 1, right? Equals 1 joule. So my net work is equal to, the sum of all these. So 6 plus 4.5 minus 1/2. I forgot to put the negative on this guy because he's underneath the x-axis too, plus a -1. So 6 plus 4 minus 1/2. Okay, so this would be 6 plus 4 minus 1/2 is 6 plus 4 minus 1. This comes out to be 9 joules or meters. Okay, so the network is the sum of all those areas. If any areas are below the x-axis, be sure to make those areas negative. That's frictional work. Okay, this one is like our lab we just did. What's the spring constant of a spring based on its force versus? Okay, that's K, and that's simply the slope of the curve. So we could do this. We could do the whole graph if you want. That'd probably be easier, but I'll just pick that. K is the slope. So it's a rise, 60 over the run, 0.6. So that's just 100 newtons per meter. You could have done this triangle instead if you want. Right there, 20 divided by 0.2 is the same thing. Okay, so what's the elastic potential of the spring when extended based on the graph above? Okay, well, I can just go like this, and then, okay, the area under F versus X graph, the area is going to be the work done. The work done is the change in elastic potential energy. So really, I'm just going to find that area right there. So the work equals the change in EPE. Looking for, I'm assuming it started from rest, so EPE is EPEF minus EPEO, original, but I don't have any original force at the beginning right there with no force or displacement to the spring. So basically, elastic potential energy is the work. Work is figured out by doing the area under the curve. So whenever you have a spring, the area under the curve is the EPE that is changed by. So that's work equals KD squared over 2. That's the equation for EPE. So that'd be, the K is 100 times the D squared. That's 0.7 right here. And then divide by 2. So 50 times 0.7 squared is 24.5 joules. So that's what the EPE is, or change in EPE, because they both equal.